This is an interesting topic that you usually wouldn't see on Java events, and this is a Hail Mary, I say, when I submitted a lot of talks to this event. This is the one that the committee accepted. So, okay, let's see if this is something useful to you guys. So this is musings of how enterprise Java can also work on gaming development. And this is mostly about reusing knowledge across industries. So a bit about myself. I'm Fabio Turizo. I work for a company called Payara. We're sponsoring this event. I won't do a lot of sales pitch on this talk about Payara. There is a booth if you're interested in what we do and the products that we are making available to the developers and management in general. Stop by. We have some cool swag that we're giving away to you. I don't do a lot of social media, but if you're interested in connecting with me, I highly recommend LinkedIn, which is usually what I mostly interact to as well. So just that one slide about the sales pitch. Sorry about that. We are strategic members of the Eclipse Foundation. Payara implements basically a Jakarta MicroProfile compatible runtime, which is something that you can use to develop enterprise Java applications for a myriad of businesses. If you're interacting with the banking industry or if you're working on a sales company of some sort, Payara, it's something that you can use to implement whatever backend you have in mind. It's usually highly transactional, highly solid and robust, and something that I would usually talk more in regular standard talks about enterprise Java. But that's not what this is about. Let me do some disclaimers first. So I am not a game designer. I'm just a guy doing this crazy talk and see if you guys don't object too much about it. But if there is a game designer in the audience, I'd like for them to raise their hand. OK, so either full transparency or someone wants to go incognito, that's fine. Still, if I'm saying something crazy, if you're working game development and you say, oh, this guy's saying some nonsense, please let me know. Absolutely. More than happy to receive the feedback. Not I have worked on big gaming projects yet. I have worked on small projects in the past, anonymously, I would say, nothing that was mainstream or anything that made any attention. But this is an interest of mine because I game a lot. But in my personal time, whenever life allows me to, because it's difficult nowadays to find time for yourself between family, responsibilities, business, etc. However, I have done a lot of my career on enterprise Java. I have some grasp of how the challenges that you resolve on an application that has to deal with the most basic stuff on an e-commerce site, for example, building a shopping cart, how that translates to Jakarta or to Java development in general, how you resolve or solve problems like that. And that's good because I also have experience supporting service backends. When you have a company that calls you at 2 a.m. on a Saturday saying, hey, my thing's down, everything's on fire, my customers are angry, help us, then OK, you have to do a lot of troubleshooting, a lot of investigation, and some, let's say, prerogative experience that will serve you to, oh, I know what's happening, go flick the switch, everything's good, go back to sleep, something like that. So I think that that experience can be translated into implementing a gaming backend or something that you can use for infrastructure in gaming. So this talk is basically focused about me sharing those talks with you. I wanted to prepare a really cool demo. Unfortunately, life didn't allow me to do so. So on the moment, this is just conceptual. In a future iteration of this talk, I would like to show some really cool demo. I wanted to build something using Doom. I bit more than I can chew because Doom code is it's interesting in a sense. But maybe in the future, that's something I'm looking forward to. So online gaming in general has some interesting components. So you might recognize some of the games shown on the screen. The entire point of these games is that they have either multiplayer built in as some. Oh, is that a problem?
No. I just wanted to make sure it wasn't.
Yeah, your screen's blinking.
It was blinking, see?
OK, well, that's part of the invention. But yes, I noticed that it was blinking before. It wasn't that annoying, but OK, good to know it was resolved. So these games, you may have played some of them. The first one is super popular. This is the only screenshots that I will have with games on these slides because I don't want to get sued by this company, so I'm not going to risk it. So there's only this one. But all of these games were built with multiplayer as a pillar or cornerstone of their gameplay and what engages with players in general. And some of them have that built in as a secondary aspect of it that drive some engagement. So Elden Ring, super popular game. It's not necessarily built for multiplayer. Interestingly, they are now doing a game that focuses on that, but it has some collaborative and competitive of sorts built into it. Multiplayer that you can do if you want to play with your friends. Well, not necessarily that easily, but if you want to play with people, you can do that. All of those games have in common that there is some backend infrastructure that handles all of that, servers. And what you will usually hear about is when those servers are down on a weekend, players and people will complain loudly on social media about that. And yes, companies behind that will probably do some sort of compensation in order to prevent that. Designing a gaming backend requires some questions. The first one is the authority model that you want to use. If you are familiar with gaming lingo, in a sense, the authority model is the way that you want to build your multiplayer experience. Do you want every game client, that is the application that the player is running on the mobile phone or the console or the PC, or there be a headset connected to PC, does it hold the entire truth about the game? Everything that it manages, from game state to player state to how, oh, it's still flickering, but okay, if it becomes a lot of, if it becomes more annoying, let me know. But in that sense, the client is what makes the player or the user trust that the data can be exchanged freely. So clients communicate with each other, and okay, if someone wants to cheat or they want to do some sort of cheating with a multiplayer game, they technically can do that because there is no authority validating that information, which is something that if you handle enterprise Java, you know that you have to treat the user, apologies for that, you have to treat the user like an idiot, that they will find a way to break whatever backend you design. So you have to validate inputs, and you have to validate information integrity and confidentiality by yourself. That translates to the gaming experience on the server authority model. The server is the truth. If the server is online, it's receiving inputs from the players. The only thing that it's doing is sending updates back to the client. And the client is responsible for rendering those updates, making sure that the player has a good experience, and so on. When choosing a server model, are you aware of its costs? Because if you're implementing a gaming backend, if you put servers into whatever cloud provider you want to choose, or if you're doing self-hosting of some sort, all of that is money that you have to factor into that. So if your budget allows it, cool. How accurate is the client synchronization needs to be? And that depends wildly on whatever gaming genre you're interacting with. If I'm implementing, again, like Fortnite or Call of Duty, synchronization, which is real time, it's extremely difficult. And it's actually not something I would suggest using Java for. And what type of data is exchanged? Most of these games exchange little data between client and server. Because as I said, it's mostly about an input. A player press a button, or they executed an action that the client and the server recognizes, and then they act based on that. It's not like the traditional enterprise backend where you have a lot of data that can be exchanged, mainly personal and business data. So you have to factor that in play. Most of the online gaming features of nowadays fall into this. And the idea is that you can use Java to implement most of this. Ideally, what you would want to do is implement what fits your needs. Java has its strengths and weaknesses that I will touch in a bit, but mostly it suits most of this. That is managing servers, lobbies, rooms, in the sense that, okay, you open a multiplayer experience to multiple games. Let's say hundreds of players could play a game concurrently. They need a way to coordinate each other how to play. Number one. If you're doing cooperative or collaborative or competitive gaming, they need a way to design, or you need a way to coordinate that as well. Game state generation is important because, as I said, on the authority model, the server is responsible for managing the entire truth about what is happening in a game session. So that server needs to be able to regenerate that data if it's lost in real time. And there is a centralization of game data and game state. If a player wants to cheat because they want to build, or they know coding and they can interact with a client, especially if it's written on a easy to understand language like JavaScript, they will be able to. So the game server, and in this case, whatever you implement, needs to be able to cope with that. Unusual metrics, and Java is wonderful with metrics. When you're interacting with metrics and you have leaderboards, or you want to implement game challenges and data that you want to send from the server to client, that's something that you can do as well. Regular updates, it's something that has become prevalent in gaming nowadays. Games get updated regularly. Whereas in the past, you had updates every 3 years, and there were big updates that had to be selectively downloaded by users. Now a game updates basically every other week. So you need to also take that into consideration as well. So making games is hard. And before any code is written, and again, this is not part of the talk, but this is something that as someone that plays a lot of games understands, there needs to be a lot of creative thinking. Before even writing code, you need a good idea. You need to make a fun idea. You need to make the experience good for players. Because if something is not fun, why would anyone bother that time with it? They wouldn't play with a game if that is not something that it's enticable or it's not attractive. So game ideas and basic design go first. Before writing a backend, make sure that you have a fun idea, implement it. And again, this is not necessarily the point of the talk, but I want to reinforce that point because it's important as well. On good software design, you always need to have a batch of requirements and a set of use cases. On gaming, that translates to a good design and a good idea that you can go around with. As I said, if you're implementing a multiplayer game with a lot of concurrent players, if you're implementing something that 2 or 3 player people are at the same time, you don't need an authoritative server. The client can take care of that. And again, if a game starts to scale up, that's something that you could do. So once multiplayer is in, basic software architecture is what will help you implement a good and robust backend. And that starts with, as I mentioned, the strengths of Java. Java is a great language when you're continuously exchanging data between client and server. And if all of you have developed with Java through the years, you will know that because most of Java's strengths is implementing services and clients that exchange data freely between each other. So how that does translate to a gaming backend? Well, as I mentioned, gaming backends don't exchange too much data, but they do a lot of continuous exchange. So that's something that you can do as well. And the important part is that Java has a lot of support for both synchronous and asynchronous communication. If I need to send a message from server to client and just act immediately and act when the response to that message comes along, then that's something that Java can do easily. And there are a lot of protocols, libraries, and implementations that you can play around with it. Java also is really good for performance server processing. If you need to process millions of responses at the same time on a server, Java is more than suited for that. There are frameworks, both Jakarta, Spring, Quarkus. Any enterprise Java backend is suited to doing that. Absolutely. And that is due to the multi-threaded model that most of you are familiar with. Multi-threading is something that is not necessarily easy to understand at the beginning. It takes time, specifically with everything that comes or that has come in Java recently. So when you are building a scalable architecture, that's where you would use Java. That's something that we all are familiar with. Java is terrible at implementing game clients, I would say. It doesn't necessarily mean that it's bad. If you want to implement a really small game that doesn't necessarily handles a lot of real-time input, there are a lot of good libraries on Java. There is JavaFX, there are OpenGXL implementations and wrappers around. There are other Linux-based game graphic interaction libraries that you can use. But again, there are better options in the market. And I'm not going to tell you use Java if you want to implement a gaming client for a highly competitive multiplayer game. Absolutely not. There are better alternatives in the market. Godot, for example, is an open source project that has a lot of traction because it's well documented and it has a lot of cool things both on 2D and 3D that you can build on the client. So maybe use that if you want to. But if you're building the backend of a multiplayer gaming experience, Java is well suited for some cases, as I mentioned. So let's focus on 4 aspects of what I want to talk about on this backend implementation. The first one is communication. How do you communicate between server and client? There are some options. And exchanging data across server and client is important because most of the data that you will be exchanging will be continuous. It will be small chunks, unless you're exchanging videos or you're doing some sort of streaming. There's concurrency. Multiple players are accessing a shared state in real time. For example, let's say that they're playing Fortnite. Fortnite has a map that is rendered in real time. All of these players are interacted with items, objects. The map itself is changing concurrently along with what those players do in a gaming session. So, hey, all of that needs to happen at the same time and in real time or quasi-real time in a sense. So hey, there is something that you need to do about that. Memory and storage. Well, all of that data needs to end up somewhere, right? And specifically, as I mentioned, one of Java's strengths is its memory management. You don't need to worry about that. Java has something called a garbage collector that will handle all of that for you as long as you know what you're doing. So it's important to take that into consideration. And finally, scaling. Okay, I started my game with 5 players. It grew big, and now I have maybe thousands of players playing at the same time. Maybe there is summer break coming, and there are 10,000 of players playing on a Saturday, and they're complaining that the servers are down, and I lost my chance to actually make something really big. So preparing for scaling is extremely important. So a basic game service architecture is not that complex. You have servers. How you implement those servers is technically not difficult. You can choose a cloud provider, use Amazon, use Azure, etc. Those servers contain a lot of memory data that needs to be coordinated in some way. And as I said, whatever client the player is using, if it's a PC, or if it's a game console, or if it's a mobile phone, that doesn't matter. What is mattering is that it's sending actions to the server. The server is just simply listening on those actions by an authenticated or joined player to a game session, and it's just sending updates. Something happened due to the input of this player, and you need to consolidate that information in one go. And every server will hold some game state in orange there, and it will hold player state. So the game state is shared across a gaming session or a multiplayer game, and the player state is, of course, concurrently held by every player that has joined the session. So you need to coordinate that data. And at some point, and this is important, you need to store whatever information is relevant for your game experience, in a sense, or for you as a maintainer of that experience, into a database. So whatever you choose, if it's a relational, traditional, SQL database, or if it's a NoSQL solution, if you want to use file storage, again, that's something that you could do, but you need to move that data to that point. So that server architecture that you have seen on a Java backend is perfectly suitable for a gaming backend. And let's start with the communication protocol choices. So on Java nowadays, what you would do is usually use REST APIs when you want to implement something that you expose data to from the client to the server. On a gaming experience, a traditional REST architecture, it's not that useful because that is a lot of overhead with number one, HTTP. It's based on TCP, and TCP has a lot of overhead between packet confirmation and acknowledgement. That will add to an overhead between the player pressing a button and expecting something to happen. And well, on top of HTTP, REST services architecture, also it's based on a lot of JSON serialization and deserialization, will add a lot of overhead that a player doesn't need to deal with. So there are some 3 responses that I consider. Actually, one of our customers implemented their backend using WebSockets, and they were really fine with it. But WebSockets, which are very simple to set up, they're also based on HTTP. Want to be specifically, but it has a lot of simplification of that overhead. There's also gRPC, which is fully binary. It's not a super popular protocol, but it's something that you can use as well. But if you want to go crazy and you want to implement something like a looter shooter or a gameplay with real-time or real-time, let's say, synchronization, you have to go lower and use TCP or UDP. In fact, most gaming engines that are designed to handle that real-time synchronization use UDP because, as I mentioned, TCP has a lot of overhead between packet acknowledgement and confirmation. UDP is better. But with UDP, you have a lot of things you have to deal with it as well because if you lose a packet, that's gone. You need to resend it again. So for code on WebSockets, and let's actually do some overview of the protocol. Is a very simple duplex communication channel protocol mechanism. You have a client and a server. The client joins a WebSocket session, a channel is established, and then client and server can exchange messages freely between each other. WebSockets is actually interesting because the technology is fully developed, it's mature enough, but I don't see many people using them. I see people, not necessarily on a gaming backend or an enterprise backend, I see people going clever when they say, oh, I need to establish some stateful communication mechanism between client and server, and they design something using web sessions and using some crazy servlets or using some sort of a tracking identifier, and I say, why don't you just use WebSockets? It does everything for you. You don't need to worry about anything. It's built on top of HTTP, fully symmetrical, and has support for asynchronous communication. If I send a message from client to server or vice versa, you don't need to worry about what action comes next because the client will react on that message and the server will do as well. So traditional communication will be a client connects via WebSocket. It usually will do some sort of authentication because in a multiplayer gaming experience, you will like players at the very least to be identified within the framework, depends on what you want to achieve. And then you will have the player joining the session, sending the actions, and then the game sends back the updates. That's the thing. It's always that, let's say, exchange between the player action and a game update. And hey, the game might be doing some things. As I said, game maps or map data will update on itself. It also needs to update players on what is happening on the background. So how will you do that on Java code? It is simple. If you don't recognize this, this is the WebSockets implementations on Jakarta. If you do Spring, Spring has something similar. So what you would do is just implement a game server saying, hey, this is a WebSockets endpoint. And I would define a method called an open that simply says when a gaming session starts, you will have a player joining. You just simply need to find that player somewhere. So you can just do that using, oh, sorry, I'll go back. You can do that using a player service or whatever you. Where is my cursor? Come on. There we go. OK. It's a slight delay. OK. There is a player service that will allow you to find that player based on an ID or a cookie or whatever you want to implement. And then you do some validation. Oh, is that player does actually exist? Cool. No? OK. Then whatever happens, send an update. And that update is just simply sending the information back. And the session objects on the WebSockets implementations of Jakarta has distinction between asynchronous and synchronous sending. And I want this to be asynchronous because I want to send the game update and not keep the player waiting around. I want it to be fully asynchronous. So I just simply do session get async remote, and I send the message. In this case, this implementation uses text messages, which is not necessarily bad. But in some cases, that can be a bit too much of an overhead. So the WebSockets protocol also supports binary data. Binary data is Lina, who here actually deals with binary data encoding in Java, or has dealt with that. OK, fairly good people. I had a talk when, not something about this, but something similar. No one was doing that. Everyone was doing JSON serialization or some sort of text manipulation. I was like, do binary. In some cases, it's leaner because you will have less overhead. And there is no noticeable, let's say, savings you can get on a simple benchmark. So the WebSockets protocol supports that. The only thing that you have to do is just, instead of a string, you use a byte buffer. You encode and decode that information. So for example, a packet on a WebSocket could be, oh, a player action is just a code, a binary code. You have, in that case, well, like bytes of choices to use from, a separator, and then a content. What happened, or what the player is doing, or what the game is doing in that regard. And you decode that, and for the game update, you do the same thing on reverse. But Java developers, well, before that, what this would look on the client side, if, for example, if you're using WebSockets, the JavaScript language already has native support for that. So if you're implementing your gaming client on JavaScript, that's something that you can do. You would just simply open a new WebSocket. That's an object on the JavaScript API. Connect to the server. In that case, the handshake always happens first. I connect to a specific URL. And if you are a Java developer, port 808088 is a staple. So hey, that's where my server would be. Or if you're using a CDN or DNS distribution network, you would use that. And then you define, OK, I want a non-message listener that says when I get a new packet or a new message coming from the server, I want to do something. So you will process that game update. What would happen is, OK, I go grab that update, render that in real time on my gaming client, make changes on the graphics online, and then do some updates on the memory internally, and that's it. And then repeat that action consistently. However, we Java developers, well, come on, I assume it was the next one. So there's also code to do that on the gaming update as well. So you can process that update by just simply checking out, in this case, on JavaScript, you could do this, technically just slice the data from how you receive it. And because it's binary data, you can just decode it in a simple way. There are other ways to decode and encode binary data on JavaScript. But again, this is just an example. You don't need to follow this up to the letter. There are multiple ways of doing that. It's not difficult. If your gaming client is not implemented using JavaScript, if you want to go the Java way, because again, there's always an option. There are multiple WebSockets implementations for clients on Java. There's also a lot of implementations for WebSocket on Python, on C++, even if so, if you wanted to implement a native client on C++, that is a bit faster rendering real-time data. So Java developers love structured data. One of Java's strengths is that we can technically model everything into a class, even though sometimes it's counterproductive to do so, but hey, it's something that you can do. So you can also implement a customized encoder and decoder. Instead of having me to manually grab a byte buffer and destructure that information, I could just simply tell the runtime to do that for myself. And that way, you actually can codify all possible player inputs. And the way to do that is that you can implement on the WebSockets API something called a decoder. A decoder and an encoder, there are classes that just simply receive bytes and send bytes. And the decoder will just simply, OK, I get a byte buffer, receive all of the information, and then return everything in a nice wrap class called player action, which is something that I can implement. Yes?
OK, so is this possible in, let's say, a synchronous way where you do not send the whole message as one message, but you send it like 8 bytes by 8 bytes by 8 bytes?
Absolutely. The question is if you can split messages in multiple byte sequences. Yes, the WebSocket implementation uses TCP underlying, so technically it has a necessity to track packets in order. So you can do that. Well, that's on you. If you implement the decoder in that manner and your message is split in multiple ways, you need some way to track that. So again, player inputs shouldn't be that big. If you have a lot of data you're sending as a player input or a game update, then you might need to rethink your solution because it should be as short as possible. Remember, this is making the player wait. So if you send in multiple chains of messages, then either they're consistently done fast and you have a way to track them fast, or you just simply send one packet that is as small as possible, encoded, because it should be in binary form as well.
So,
yep.
So the game action is like press a button? So like if it's
Yeah.
in real time, it's like you press D or something?
Most gaming backends that actually have codified player actions, because as I said, if you just simply receive the input, that could be a way for the player to cheat. If they say, oh, I press a button, and immediately the next nanosecond I place the next button, then if you do not validate that with some sort of, let's say, tracking, then the player could just simply cheat. So it's it's easier just to codify on the client. The player press up D, for example, and then translate it to a move action. Move one space up, for example. So that's what you send to the server.
This is also cheatable.
In a sense, but if you're tracking what the player is doing on the back end, then you could validate, could the player move up? For example, they could be at the border of the map. They say, I move up. If you're not validating that on the server, then that's something that you cannot do. But that is easier because instead of tracking the game, let's say, or the player input or the controller input or controller mechanism input, you're just simply tracking what they can do. Both solutions are good, personally. And I look a lot of gaming client code, not written in Java, of course, but most of them, basically, if they're not in real time, they usually deal with player inputs because it's quicker. But if not in real time, like, for example, a turn-based strategy game, they usually just deal with actions. Yeah, and it's easier that way.
In real time, do you make your quant to predict what's going to happen?
Oh, well, that's beyond that topic, because as I said, if you're implementing something in real time, you have to low level, and you have to go lower. And I have an example of how to implement that, basically. But that would be too much, in my opinion. For Java, I would need a lot of experience to actually give you an informed opinion of whether or not you want to do that. It depends at the end how competitive and how fair you want the gameplay to be. Because if I press a button and I expect that reaction between half a frame or half 2 frames, for example, I'm talking about something like a shooter or a competitive arena game, for example, then yes, of course, you want that player to receive input and feedback as soon as possible from the input that they gave.
I mean,
Yep.
For a round-based game, I can imagine that it's easy to qualify an action because it will not disappear somehow. It's a round-based game, so you will say, yeah, I go to the right.
I do have that on. I do have that on a slide a bit later. So.
But if I have a real-time game, the monster could disappear, and if I say like I slashed the monster, if it disappeared, it's not slashed.
Yes, and again, that will be rendered as a correction on the client, and the player would say, "What happened there? I did something, and something corrected itself." And again, there are multiple ways to deal with that. It's always important to communicate those to the player, in my opinion, because if the player doesn't know what happened and they're just figuring out that happens repeatedly, then that experience is not good.
If you have a lot of latency, for instance, in some of the
Yeah, sorry, I have to move on because I have a lot to talk about. So, just going to skip through this code. You will have a game updater encoder as well. It will do the exact same thing, but on reverse. It will just simply receive a class on Java, an object, and decode as a binary buffer, and that's what it will return. So the server endpoint, in that case, it is easier because the only thing that you need to tell the server endpoint annotation is here are my encoders and decoders, and you can use as many as you want for as many objects as you want in that case. That is a preference to the Java developer that likes to play with structured data. So about gRPC. gRPC is an interesting option because it is a powerful protocol that not many people are aware about. It isn't technically not standardized. It's a technology that was designed by Google and was open source in a way. It's built on top of HTTP2, so it has more overhead to talk about. In fact, most of the investigations that I did don't technically like gRPC unless you're doing something really simulated, like a turn-based strategy game or a turn-based game of some sort, when you don't worry about real-time synchronization. In that case, you can go with gRPC because gRPC is a bit robust in the sense that the streaming of data is quicker, the establishing of the connection is slower, but changing data once you have a session established is faster. Also, gRPC allows you to be a bit more strict on how you define the data that you send. This is for the pure Java developer that loves a lot of definition and structure. So on gRPC, you will have something called a definition file, .proto, because the gRPC communication mechanism is based on something called protocol buffers, which is binary exchange data mechanism. So you would define what are your messages, inputs, and responses, and put those on a file, compile that using whatever utility you have. On Java, there are a lot of nice Maven plugins that allows you to just simply grab this file and generate everything for you. And then you can just use that class in the whatever implementation you want. So you have something like the game server that I showed you before. In this way, it's implemented using gRPC. And in gRPC, you use a stream observer class. So you just send updates as part of a streaming channel. You don't need to send and resend communication. You have a constant access to the streaming, let's say, well, to the stream open from server to client, which is really good in a sense because you don't need to confuse yourself too much about the game flow. But as I said, gRPC is not necessarily performance. So if you don't worry about real-time updates, then gRPC could be a really good solution. As I said, real-time games will not necessarily like this because, again, there is a lot of processing. That doesn't mean that you can do on Java. And this is super crazy. You would do this on 2025. But nothing prevents you from writing code that just uses a datagram socket. And for those of us oldies that implemented code since 20-something, when there was RMI and a lot of old Java communication mechanisms, hey, you can open a socket, listen on a specific port and receive the data and have to write all of the code in the world to manage that communication. That's something that you can do in Java as well. I would like to do some benchmarks on this and see how quick you can get between an implementation that uses WebSockets against UDP, but the literature online across not just Java, in general, likes using UDP better. In fact, if you go and look at some of the code of open source fighting games that are online, all of them use UDP when they are doing some synchronization. Of course, it's easy to synchronize what happens between two players, but they absolutely agree that no, TCP adds a lot of overhead, around maybe 30 to 40 seconds, I read in general, and I would like to put that as a quote, but I run out of space on the slides. So that's something that you can do as well. Nothing prevents you from creating a singleton component that once starts, opens a datagram socket on a specific port, and it's listening for packets. So every time that you receive a packet, you will have to do the encoding by yourself. It's just binary data. Extract it, do something, and then send a packet back. If you lose that packet, well, that's on you to resend it. There's no way for you to know if the client got the packet. So again, that network, let's say, constraint limitation of synchronizing game data, it's something that you have to implement on yourself. So over here, you will have the code for processing that packet. It's very similar. Again, the only thing that you have is just a datagram packet, and that's how you would send it. So REST services can also help as well. As I mentioned, some specific cases are for leaderboards. For example, you open the game client, and in that case, you want to see the metrics of how many players are on the top 100. That's just a REST call happening. You get the data from the server, Get it once, show it on screen, and you're done. You don't need to implement WebSockets or gRPC. You can just simply get the data easily. It's metrics, so you're only reading data. You're not manipulating data on the game server in any way. The way to do this, you're all familiar with how to do REST services on either Jakarta or Spring. In Jakarta, you will implement a REST service endpoint, and you just simply send structured data back, and you just hope for the JSON serializer to do its job. That's it. Easy. So let's talk about concurrency. The main challenge of concurrency is how to access shared game state. Something is happening, and two players press a button at the same time, and the server needs to decide who goes first. So how to process information in parallel is important, and Java does this really good because, again, one of the staples of Java is synchronization. How it's done is, well, through the ages, synchronization has always been a challenging in teaching because it is a bit tricky to get it. But the important thing is that player interaction is always processed in parallel and resolved by the server, depending on how your game logic is implemented. That's it. How you handle that, you need to take that into consideration while you're implementing. So the game type or genre will decide that. If you're implementing a turn-based game, concurrency solved with you because there is only one action at a time. Nothing has to happen in parallel. There you go. You solved the problem. That's it. If you're doing something a bit more close to real time or close to real time, then you need to quickly access share state in an action and then free whatever synchronization mechanism you're using in the span of a millisecond, I would say. So something like cooperative games don't necessarily would suffer a lot from this, because if two players are gaming with each other in a session, two actions done by something that is happening cooperatively don't necessarily harm any players, and they feel like there's progress. If that's competitive, and that's where the actual thing is, like a shooter or a survivor or an arena fighter, there needs to be some consolidation, and every game will deal with this differently. How would you handle this with Java? And as I said, a turn-based example is simple. The only thing that I have is a game instance. It starts, for example, let's say that we have a game instance that has players running in order. So all players join the session. You start the game by shuffling the player order, and then you have a player starting, and you say, OK, start. Send me what you want to do to your turn. If someone else sends actions because they want to cheat, well, that's easy. Are you the current player in turn? No? OK. I'll send you something back. You can't do anything. The player in turn is the one that decides what happens, and then you simply send a game update back. Very easily, there's no concurrency happening because there's only one action happening at the same time. However, when you are doing game data access, there needs to be something managed by a singleton component. That game server regulates everything happening to every player playing concurrently, so modifications to the game instance are done synchronously. Other operations should be done asynchronously. So if, for example, let's say two players are playing a game, you update the map, and then you need to say something like, OK, there is data that I need to store on a database somewhere. That action should be asynchronous, because that is just simply moving data from one endpoint to the other. But if those two players are modifying map data or something similar, they could need to do that synchronously. So the way to do that on Java, and most Java backends or runtimes, handle thread pools. And thread pools allow you to optimize that. Each action by a player needs to happen on a thread, separate from every other thread. And if you're using Java 21, you should be using virtual threads, because those are actually quicker than the standard wrappers that we had before on operating system threads. Virtual threads are faster as long as you're not doing input-output, which for synchronizing game state data, you should never do. That's why I said those actions are asynchronous. So a concurrent game example will do something like that, something like this. You have a game access coordinator. You have a number of games happening concurrently. You could store that on a concurrent hash map, just as a way to put that in a, doesn't have to be a concurrent hash map, but just doing that by example. But let's say that you have something happening between two players at the same time. How do you coordinate that easily on Java? You can use logs. Whoever here uses logs on their applications by hand? OK, do you have regular problems with those? OK, so yes, no. Logs are actually very easy to understand, very hard to get right, let's say, on a scale basis. So a log is just simply a way to prevent program flow from completing until the log is released. If you never release the log that you acquired before, you are in a deadlock situation, so you need to be careful about that. But on a gaming scenario, that's not too difficult to handle. You just simply receive or acquire the log when you execute a player action. you get an update, and then you release the log immediately. That's it. That means that if two players press a button at the same time, by a matter of milliseconds, there will be someone acquiring the log before the other. You let Java decide who, and then lock, decide that, and unlock. That unlock action on a virtual thread should be lesser than 100 milliseconds by benchmark, by modern benchmarks. And I haven't checked that metrics, but it should be around that. If I'm not moving data or doing input-output on a virtual thread, that's super quick. And that's why I suggest this is an area. That's something that we do in Enterprise Java. Many users are not aware of this solution where they can use logs to concurrently update data. They usually tend to fall back in either synchronized blocks, which technically do something similar but are a bit less performant, or they do something different using atomic structures or using, let's say, self-implemented solutions. So once I release the log, that's where I need to do whatever operation comes next asynchronously, because, hey, that player is waiting. They press a button, they need something back in some form. So, okay, I consolidated the data, send an update, and whatever happens is done asynchronously to return flow, and then I give that player the update. Yeah?
What about if not using threads or virtual threads, but using asynchronous like Neo and selectable channels, where you subscribe to the network adapter for messages, and then you can get them in a queue or something like that?
I'm not sure, because that, in my head, sounds like a bit of overhead. The log is very simpler.
The overhead should be in the virtual thread because we have carrier in virtual thread, and the other way around we have selectable channel where you watch multiple descriptors and they say you 20 of your descriptors have new events, you can process them.
Could work. I don't have the data to say if it's better or not. That's simply solved by doing a benchmarking testing out both solutions. Yeah, because I can tell you, in my head, it seems like there would be some overhead, but I will need to test it out before confirming. So for asynchronous operations, most frameworks handle this very easily. Jakarta has this annotation saying, hey, whatever is executed in this method is done asynchronously. Most of asynchronous operations have to be tied to an executor service that handles internally a thread pool. So whatever runtime you're using needs to optimize and perform some fine-tuning on that executor so that it's, for example, if you are assuming I have 1 million players concurrently that could handle actions at the same time, that sounds a bit too crazy for a Java backend, but it could happen, then you need to have an executor that copes with that load. Otherwise, it will be useless because there will be some queue and so wait time between players, and that will ruin the experience. So game state management in general is not too difficult. So this is the object that is updated within the log. You will have an executor service that is initialized and is used in order to run threads. You have some, most game backends and most gaming solutions usually do some updates based on a tick. So you have a game loop that has a tick rate that updates the game every now and then. Depends on what you implemented. On a real-time, let's say, game, that tick would be very minimal, almost like maybe less than a second. On some games, it can be a bit more lenient, but basically it's how you're coordinated, what happens in your game when your players are not doing anything. Enemies are moving around, the game map area is being reduced, or something is happening to make updates make the game feel livelier in a sense. So you need to coordinate that, and the way that you do that on a Java example is just to simply have an executor submitting a game loop task that just simply runs that on a separate thread. You only need to worry about that thread when you're closing it up, but in the meantime, that game is just simply sending updates to the players every now and then when the game loop updates. So hey, you have a game loop that is updating, it's sleeping when it's not doing anything, depending on the tick rate, and that's being done. If you implement this on a game client, it would be similar. So if you have a single player experience where the map is doing things on its own, you would just do the same solution. So it's not that different between client and server in that sense. Okay, so memory and persistent storage, and this is important because, as I said, you need to manage all of this in memory. All gaming backends manage all of this in memory, and this is important because on Java backend development, usually you are worried about moving data from memory to a storage as soon as possible because that's in your interest of not losing that data. On a gaming backend, that's not a big deal because, again, it's a game. It's not the end of the world if someone lost their Call of Duty session to other 6 players, okay? No one lost any money. They've lost time, in a sense. They felt like that waste, but hey, no one gets sued for that. Well, depends if it doesn't happen at scale.
If it's a tournament, probably you'll get
Oh, well, no, don't. Let's not go in there. Yes, if it's a tournament, you lose that. OK, so you need to persist game data quickly, but that doesn't have to be happening concurrently. So what you do is usually, OK, you have a component that handles persistence. The only thing that you need to do is, OK, once the game is finished, I just asynchronously tell the game, let me record that separately. And then what happens is that you need to save that information. A good solution sometimes when you are worried about losing game data but not affecting players is to use a distributed cache. And this is interesting because not many people use distributed caches. Nowadays, this is a bit of a crazy idea between crazy ideas. I've been testing this. It's actually worked well when you are implementing it correctly. But that distributable caches, oh, I think that I ran out of time. OK, so try to do this very quickly and summarizing, unfortunately, because I lost track of the time. But ideally, what you would happen at the end is that you would implement a component with a distributed cache that will allow you to save game data. You will move that data when you're initializing the game service. And then whenever something happens, you just simply coordinate and get that data from there. And using a distributed cache is not that difficult. There are many powerful solutions in the market. There is Hazelcast, there is InfiniSpan, there is Oracle Coherence. If it's something that you want to use for free and open source, there's also Redis, which is very lightweight. It's something that I wanted to implement in my example. Unfortunately, I did not have enough time. Just to quickly finalize this step, between regular SQL and NoSQL databases, my recommendation, use NoSQL because it is flexible. Game data is usually evolving. While you have a version 1 of a game doesn't necessarily mean that it will be consistent across games. As you introduce features, game mechanisms, and you try to get players, attached to your game, you need to add more structures and modifications. And NoSQL is better for that. OK, so unfortunately, I ran out of time. But that's 3 out of 4 aspects, so I think that we did good. Just to quickly show, in summary, game development challenges and solutions benefit from enterprise development techniques. What you do on Java Enterprise is really good for game development. The only thing is that you don't need to worry about certain things, and you need to worry about others. A game backend is not that much different from an enterprise backend. There's nuance in how you design it. At the end, it's how you want to design your solution, not necessarily what you want to achieve. And this only applies as long as you are minimizing frustration for players. So that's, at the end goal, what you want to do, have a really good experience for people in general. And yes, that's it. Thank you. Sorry for the rush.